Let me start with something simple but powerful. Imagine you have 5 replicas of your database running on 5 different machines. Now suppose 2 users send 2 different write requests at almost the same time. How do all 5 replicas decide which write request comes first? How do they agree on the exact order? And more importantly, how do they ensure that they all agree on the same truth? Replication copies data, but consensus decides what the truth is. Today, we're going to understand consistency models, quorum systems, and the consensus algorithms that make distributed systems reliable. And by the end of this video, you should clearly understand how systems like distributed databases maintain agreement even when machines fail. So before we talk about consensus algorithms, we need to clarify what consistency means. In distributed systems, consistency describes what guarantees clients receive when they read data. Let me give you a scenario. You update your profile picture, and immediately after that you refresh the page. Should you always see the new picture? If the system guarantees that once a write completes, all future reads return that value. That is called strong consistency. Strong consistency makes the system behave as if there is only one copy of data. Even though replicas exist, there is an illusion that there is only a single source of truth. Now consider another situation. You update your profile picture, but for a few seconds, some users still see the old version. Eventually, all replicas synchronize and everyone sees the new picture. This is called eventual consistency. Eventual consistency allows temporary inconsistency but guarantees conversions if no new updates occur. Now let me ask you something. If you're designing a banking system, would eventual consistency be acceptable? Probably not. But if you're designing a social media feed, would strong consistency everywhere be necessary? Maybe not. Consistency is not about right or wrong, it is about trade-off. Now here's the real challenge. In distributed systems, machines fail, networks delay messages, packages get lost. So how do we guarantee that replicas agree on the same sequence of operations? This is called the consensus problem. Consensus means that a group of distributed nodes agree on a single value or decision, even in the presence of failure. In replicated database, that value is usually the next log entry. If 2 replicas disagree on log order, their states diverge. Once that happens, the system is inconsistent. Consensus algorithms are designed to guarantee 3 critical properties. First, only one leader is active at a time. Second, once a value is committed, it is never lost. Third, all nodes apply committed entries in the same order. Achieving this in an unreliable environment is extremely difficult. Before we dive into specific algorithms, we need to understand quorum systems. A quorum is simply a majority of nodes. If you have 5 replicas, a quorum is 3. If you have 7 replicas, a quorum is 4. Now here is an important mathematical property. Any 2 majorities must overlap. This overlap guarantees safety. Imagine a write is committed after 3 out of 5 nodes acknowledge it. Later, the leader crashes and a new leader must be elected. That new leader also needs vote from the 3 nodes. Because any 2 group out of 5 share at least one node in the new majority knows about the committed write. This is how quorum systems prevent data loss. Now we move on to one of the most famous algorithms in distributed systems, Paxos. Paxos was introduced by Leslie Lamport and is considered a foundational consensus algorithm. Its goal is simple in theory. It ensures that a group of unreliable nodes agree on a simple value. At a high level, Paxos works in phases. A proposer suggests a value. Acceptors vote on proposals. If a proposal receives majority support, that value becomes chosen. The key safety property of Paxos is that once a value is chosen by majority, no conflicting value can ever be chosen later. That ensures consistency. However, Paxos is often considered difficult to understand and implement correctly. While it is mathematically elegant, its complexity led engineers to look for something more practical. Now, Raft. Raft was designed to make consensus easier to understand and implement. Instead of presenting consensus as a complex abstract protocol, Raft breaks it into three clear components: leader election, log replication, and safety. At any time, there is one leader. All the writes go to that leader. The leader replicates log entry to its followers, and if the leader fails, a new election occurs. Raft ensures that only a node with the most up-to-date log can become the leader. This prevents committed entries from being overwritten. Many real-world systems prefer Raft because clarity reduces implementation, and in distributed systems, simplicity is not just elegance, it is reliability. Now let us connect everything. Strong consistency versus eventual consistency. Strong consistency often requires coordination through consensus. The system waits for majority agreement before confirming writes. This increases latency but guarantees correctness. Eventual consistency reduces coordination requirements. Writes may be accepted locally and propagated later. This improves availability and performance but allows temporary diversions. This trade-off connects closely to the CAP theorem. In presence of network partitions, a system must choose between consistency and availability. There is no perfect solution. There are only trade-offs. The right choice depends on your application's requirements. Now let us step back. Replication copies data. Quorum systems provide mathematical safety. Consensus algorithms like Paxos and Raft ensures replicas agree on a simple ordered log. Strong consistency guarantees immediate correctness, while eventual consistency prioritizes availability and performance. And distributed systems are fundamentally about managing uncertainty and imposing order on unreliable components. When you understand consensus and consistency, you understand the core of distributed systems. But even if your system is perfectly consistent and fault-tolerant, another challenge remains. How does it handle millions of incoming requests? If you have multiple replicas across machines and regions, who decides which server handles each request? How do we prevent one server from being overloaded while others remain idle? In the next video, we'll move from agreement to traffic distribution. We will explore load balancing at scale and break down Layer 4 versus Layer 7 load balancing, understanding sticky sessions, and examine geo-distributed balancing strategies used in global systems. This is where distributed systems meet real-world scale. Thank you for watching, and I'll see you in the next one.